Okay, so this is going to be a video on de Moivre's theorem. And de Moivre's theorem lets you take complex numbers z and raise them to some power n. Now there is a little caveat. The complex number actually has to be written in trigonometric form. And just to review, trigonometric form is z equals r times cosine theta plus I times sine of theta. And what de Moivre's theorem says is that if you raise z to the nth power, you get r to the nth power times the cosine of n theta plus I times sine of n theta. Now, like I said, you do have to have the number in trigonometric form, so if it starts off in standard form, you're going to have to convert it. So let's just do an example. Let's say that our number is 1 plus square root 3i to the fifth. The first thing that we're going to want to do is convert this number to trigonometric form. So I'm going to diagram it first. When I diagram it, I get this drawing, or something like this. So 1 in the real part, square root 3 in the imaginary part. So this is in quadrant 1. So I need to find my r, which is square root 1 squared plus square root 3 squared. Square root 3 squared is 3, 1 squared is 1, 1 plus 3 is 4, square root 4 is 2. We need to find theta, but like in our last videos, we're going to find tan theta and then work out what theta has to be. Well, tan theta is b over a. Square root 3 over 1, which is square root 3, that tells us that theta has to be pi over 3, or 4 pi over 3. But if we look at our diagram, we're in the first quadrant, so our angle should be pi over 3. So we can write our number as z equals r times the cosine of theta plus I times the sine of theta, which is pi over 3. Okay, so we're going to try to find z to the fifth. Now, if we invoke de Moivre's theorem, it says that we raise the r to the fifth power and multiply the thetas by 5. So we will do that. We'll have 2 to the fifth times cosine 5 pi over 3 plus I sine 5 pi over 3. If you can't read this angle right here, this is pi over 3. And we could convert this guy here to 32, and then we'll have cosine 5 pi over 3 plus I sine 5 pi over 3. Now this is a totally valid trigonometric form of the solution. Sometimes they want you to leave it in trigonometric form, in which case we're done. But if they want you to go all the way down to standard form, we just keep going a little bit and simplify. So we'll carry our 32 down. Cosine 5 pi over 3 is 1/2. We get that from our unit circle. Sine 5 pi over 3 is negative root 3 over 2. So if we multiply this to this, we get 16. And then when we multiply 32 by negative square root 3 over 2, the 32 and the 2 in the denominator reduce to a 16, but negative. And we'll bring our I over here. So to write this in the most basic form, 16 minus 16 root 3 I. So that number here that's raised to the fifth power, 1 plus square root 3i to the fifth, is equal to 16 minus 16 root 3i. So you'll notice that I did this entire problem in radians, but you don't have to. You can do it in degrees. So let's look at one of those. Let's look at -2 minus 2I to the 4th. So if we diagram our point, we have the real axis here and the imaginary axis here. -2 and -2 is going to be down here. What quadrant is this? Quadrant 3. Okay, so we're going to find our r, which is the square root of -2 squared plus -2 squared, square root of 8. If we reduce that, that is 2 root 2. Okay, so we need to find our theta. We'll find tan theta first. So tan theta is -2 over -2. This is just 1. What does that make theta? Theta has to either be pi over 4, or sorry, we're doing this in degrees, has to be either 45 degrees or 225 degrees. Now if we look at our quadrant here, 45 degrees is going to be over here, but 225 is going to be over here. So we don't want 45, we want 225. So let's write our number out. So we have r, which is 2 root 2, and then we'll have cosine of 225 plus I times sine 225. Now when we invoke de Moivre's theorem, it says we raise the radius to the 4th power and multiply the angles by 4. So z to the 4th is equal to 2 square root 2 to the 4th times cosine of 900 plus I sine 900. That's what happens when you multiply this guy by 4. So let's work out the radius first. Well, we'll have 2 to the 4th, which is 16, and then square root 2 to the 4th will be square root 2 times square root 2 times square root 2 times square root 2, or 2 times 2, which is 4. And then we will leave our angle alone for now. So we have cosine 900 plus I sine 900. 16 times 4 is 64. Leave our angle alone again. Okay, now 900 is not a normal angle for us. We like things between 0 and 360. So what we're going to do is we're going to keep subtracting 360 until we get down to a coterminal angle that we are actually used to. So if we subtract 360 one time, we get 540. But we're still too large. So we do this again. And this time we get 180, which we are used to. Okay, so we could leave it like this. This is a valid trigonometric form in degrees instead of radians. But let's say we want to go all the way to standard form. What we'll do is we'll find cosine of 180. Well, cosine of 180 is -1. And then sine of 180 is actually 0. So this term here is 0. So we'll have 64 times -1, or just -64. So in this problem, we actually looked at two different things. What do we do when it's in degrees? You just do the exact same thing. And what happens if you have an angle that's not in the range that you're used to working with? So here we had something over 360. You just keep subtracting off 360 until you get down to something that's normal. In the radian version, if you had something over 2 pi, you could just keep subtracting off 2 pi until you have something normal. I think this is a good place to stop. And if we need to do some more examples of these basic de Moivre's theorem problems, we can do that in another video.